So he will measure the time is equal to this, and now we can do some rearrangement. With this, I can take this equation and I can do some rearrangement to this one. So c square t square is equal to h square plus v square t square. And if I divide by c square, then t square is h square over c square plus v square over c square t squared. I can move this one here and take t square common, then 1 minus v square over c square t square is equal to h square over c square. And from here I can write that t is equal to h over c and 1 over 1 minus v square over c squared, and it will become square root. Right? It is now in square root form. Again, plus and minus in the same reasoning for this one. Now, if I look back to the situation, h over c was equal to t prime. So t is equal to what this value is. This value is gamma. 1 over 1 minus v square over c square. So it is gamma times t prime. Right? Now look at the value of gamma, that what gamma value will be. For example, gamma is equal to 1 minus v square over c square. Let's say we assume that v is approximately 0.5 c, means it's going half the speed of light. Then what about v square? It will become 0.25 c square. And what about 1 minus v square over c square? Just divided by c square, subtract from 1. So it will be 1 minus 0.25, 0.75. Right? And you take the square root of this one. So 1 minus v square over c square, square root will be equal to 0.75, square root is 0.866. And now you take gamma, which is 1 over 1 minus v square over c square. So it will be approximately 1.2. And gamma is greater than 1. Right, in this situation. Now look back to your equation. T is equal to t prime. T is equal to t prime. Now if t prime is equal to 1 second, let's say the moving frames say that the time the light took from there to there is 1 second. What the stationary frame is seeing? The stationary frame is seeing t will be then equal to 1.2 times 1 second, and t is seeing 1.2 second. 0.2 second more than the time observed by the moving frame. So what the stationary observer will say? The stationary observer will say that this clock is running slower because my 1 second, my 1.2 second are equal to its 1 second. So this clock is running slower. And the same, if we look at the reality, then we know that wherever the observer is considering its frame to be stationary. And then this observer will say that this observer is moving, this frame is moving, so his clock is running slow. They are both blaming each other, right? So that is another reference issue. But if we consider this one stationary and this one moving, then it seems that the clock of this one is ticking slower compared to the clock of this one. We can apply this one on some fundamental elementary particles, their lifetime. Uh, if I consider the decay time, means elementary particles are mostly unstable, and if I consider the decay times of, let's say, the decay time of neutron is approximately 15 minutes. If I consider the muon decay time, it is approximately 2 10 power minus 6 seconds. And similarly, of the pion is much less than this one, 9 10 raised to the power minus 17 seconds. These we are considering is means the times are different, they are fluctuating because the instability is not constant in nature, but we are talking of average time. Now if we solve this example that a muon is traveling, now this is the stationary or the rest frame lifetime. If this muon travels at a speed which is 3/5 the speed of light, the speed of light, then what will be its lifetime? So just look, means go back to this equation, and t is equal to t prime, and gamma is 1 over 1 minus v square over c square. Now if I put 3 over 5 here, cc will cancel and it will become 9 over 25. 25 being the LCM. So it will become 16 over 25, 16 over 25, 4 over 5, and 4 over 5 when reciprocate 5 over 4. So we will have the gamma value equal to 5 over 4 t prime, and we know about the t prime. The t prime is how much? Means in its moving frame, it is considering itself stationary, means so it is having the rest time here, and that is equal to t equals, put t prime 2 microsecond, 2 will simplify and it will come out to be 2.5 10 raised to the power minus 6 seconds. So it lives longer. How much? 0.5 microsecond it lives longer. And this thing was one of the remarkable achievement of the special theory of relativity, because some of the elementary particles reaching our earth, they are supposed to decay in the space during their travel, but they do reach our earth, and that was the confirmation that their lifetime extends there. Time dilation occurs in the moving frame. So this is the only confirmation we have regarding the time dilation. And then rest are the consequences of this thing, like the length contraction that we are going to find out. So now starting with the length contraction, means the contraction of space, and for that we again consider a box like that. And now here, let's say we are having a box which is moving at a certain speed closer to the speed of light in this direction with speed v, and we are having the laser now here, and the laser comes and hits here, a mirror comes here, and then from here it comes back here. Now I'm just, you can say, making it tilt in order to see it. Otherwise, it is just like coming in a straight line and then going like this, going back in a straight line. And what about the observer who is measuring the length the light has traveled? And the observer who is here in the stationary frame, who is measuring it from here. Now whether they will measure the same time or the time will be different. So let's see, if we ask this observer that how much time does it take for the light to travel this way and back. Again, it is very easy for him to say that this distance is x prime, and as it goes the round trip, so it will make 2 times of this, and he will say that t prime is equal to 2 times x prime over c. If we consider one way, then it will be just x prime over c. And if we ask the other observer that how much is their time, then what this observer is seeing? This observer is seeing a very complex situation, and this is the box which is moving. Okay. And when there will be some extension to it due to its speed, one extension and the other extension, I am plotting them in two extension because in one the light is traveling along the direction of motion, while when it will go back it will go against the direction of motion. So it will be something like this, that here is a mirror and the light, the laser comes in from here and then go back here. Let's say this is the time in which it has moved t1 distance, and here it is t2 distance, and the same velocity is the same, v is the same, but here keep in mind that this v is comparable to c. It is close to c, it is not ordinary speed. Now what he will see that actually there are, when this observer is seeing, he sees that the light is traveling in this direction, but the box is also traveling, the car is also traveling in this direction. So the light will have to go farther, and when it is back, then it is going against the direction of motion, and it will be something like this. What will be t1? T1 instant of time will be x plus vt1, because it has gone this much distance along this direction, divided by c. While t2, the time in this interval, it will be the same, x and vt2, let me write it as t2, but there will be minus sign because now the light is going against the direction of motion, and divided by c, the speed of light, because we are measuring here means the how much time the light has taken. That's why this speed is c, while this one is the distance traveled by the cart or box, whatever you name it. Now from here I can solve for T1 and T2. What it will be? It will be CT1 is equal to x plus VT1, or if I take C minus V in this side and T1 is common, then it is x, and T1 from here is x over C minus T. While from here, this one will be T2. Again, do the same practice, and it will be equal to x over, the only difference here, C plus V. Sorry, this is V, here this is V. Okay, so x over C plus V and x over this, and now the total time t is actually the combination of these two time intervals, and it is x over C minus V plus x over C plus V. And now here, if I take the LCM of this, it is C square minus V square, or C minus V into C plus V. And here what it will be? X is here, C minus V is here, so C plus V will be here. Plus, it is C minus V is here and X is here, so C minus V will be here. And what we will get here, that total time is equal to xc plus vx plus xc minus vx, and divided by c square minus v square. So t comes out to be, the Vx is cancelling with this Vx, and we are having 2xc divided by c square minus v square. So 2xc divided by c square minus v squared. And now from here, if I divide the numerator and the denominator by c squared, then divide by c squared, both the numerator and the denominator, then I will get t equals 2x, and then it will c by c squared, so 1 over c will come, so I write 1 over c here, and this one I write 1 minus v square over c square. This is just to introduce the gamma here. And now I have derived the time, which according to the stationary observer is this one. But if I look to the time which is measured by the frame here, so this observer has measured 2x prime over c. We got the values of t, we got the value of t prime as well. And as we have already calculated the time dilation factor, so from this time dilation, that's why I told you it's a consequence of this thing, that tells us that t is equal to gamma times t prime. Gamma means 1 over 1 minus v square over c square square root, okay, and t prime. So put the value of t prime here, like the value of t and the value of t prime here. So by putting these values, should I solve this one? Like t here is t, which is 2x over c, 1 minus 1 minus v square over c square is equal to gamma times gamma is 1 minus v square over c square root, and t prime is 2x prime over c, 2x prime over c.